Another source of transition in the scan chain that comes due to this clash between the previous response and the next input test vector. So, it is like this. Suppose at present the last pattern was applied to the circuit and the response was such that the most significant bit of the response is 1. These bits we do not consider, because they will contribute to that weighted transition for the when the shifting out the response. So, that has already been taken care of, but suppose this bit is 1 and the least significant bit of the next test vector is 0. So, as you know that this response shift out and this test pattern shift in, they occur parallelly. So, and then in the next shift cycle, so this one will come to go to the next cell, and this the first bit of the test pattern, so it will enter into the scan chain. So, and in the next cycle what will happen, this one will go to the next position, next flip flop, and this 0 will go to the next position. So, you see that there is a transition that is occurring here, there is a transition that is occurring here. So, this 1 to 0 transition will affect the entire scan chain. So, here is a transition, here is a transition, here is a transition, and here is a transition. So, this is a clash. So, if you consider if it is the case that the MSB of the previous response is different from the LSB of the next test pattern, so we will have a number of clashes generated, and the number of clashes is equal to the size of the scan chain, length of the scan chain. So, that way this is other source of transition that can occur when we are shifting in the test pattern. So, a clash occurs when the MSB of last response differs from the LSB of next test vector. Number of transitions created by a clash is equal to the size of the scan chain. Okay. So, that we have already seen. So, total number of transitions that are coming is equal to number of weighted transitions plus number of clashes into size of scan chain, because each clash will contribute to scan chain, the size of scan chain number of transitions. So, if we sum them up, we will get the total number of transitions given a set of test vectors and their corresponding responses, without considering the circuit itself. By just looking at the test vector and knowing the test vector and response and knowing the size of the scan chain, we can compute what is the total number of transitions in the scan chain that is going to occur. So, we do not do any circuit simulation, any logic simulation of the circuit. We straightway do this computation with the knowledge that this parameter can be used to compare between two different modifications of the scan chain. So, what are the approaches that we can build based on this particular knowledge about the transition? One thing is that test vector ordering. So, previously when we discussed about test vector ordering, so we assumed that from the test pattern, from the ATE, the test patterns are coming parallelly and they are getting applied to the circuit. But in most of the cases or practical cases, what happens is that the circuits will have scan chain and the test pattern will pass through the scan chain. So, the scan transition minimization becomes a major issue. So, by this test vector ordering, what we can do, we can reduce the number of clashes that are going to occur. How? Let us say that we group the test vectors into 4 groups, 1, 2, 3 and 4. In group 1, we put those patterns whose test vector LSB and response bit MSB both are 0. So, it is LSB of test vector and MSB of response both are 0. In group 2, we put those patterns for which the LSB of test vector is 0, but MSB of response bit is 1. Similarly, in group 3, we have got test LSB bit 1 for test vector and MSB of response 0, and group 4 both are 1. Now, after we have done this division of the test vectors into 4 different groups, we can frame a policy to reduce the clashes. Why? So, see these group 1 vectors and group 4 vectors, so they do not create any clash between themselves, because group 0, if all vectors belong to group 1, then there are no clashes, because MSB and LSB, those bits are same. So, no clash will be generated. Similarly, this group 4 also there is no problem, because both of them are 1. So, we can apply them any way. So, they are both there will be no clash that will be generated, but the problem occurs with group 2 and group 3. Two successive group 2 patterns will generate a clash. Similarly, two successive group 3 patterns will also generate a clash. However, there is a catch here. So, if you can alternate between group 2 and group 3, first the first pattern we apply is from group 2, the next pattern we apply is from group 3. So, there is no clash. So, this bit is 1 and this bit is also 1. So, as a result no clash is generated, and then again we apply a pattern from group 2. So, this previous response MSB was 0 and next test vector LSB is 0, again there is no clash. So, you see, if you can alternate between these group 2 and group 3 patterns, then again the same thing. So, we can avoid the clashes being generated. So, this way we can frame a very simple algorithm. So, for this test vector ordering under scan chain situation. So, first we apply patterns belonging to group 1, then we apply patterns belonging to group 4. So, this is done. Then we repeat until any group exhaust, apply a pattern from group 2 followed by apply a pattern from group 3. So, this way you can go on alternately putting the patterns. Of course, you can see that this group 4 is ending with 1. So, I should apply group 3 first and then group 2, because then this at one more clash can be avoided, this 1 and 1, this clash can be avoided. So, I think after placing group 4, so this should be reversed, apply a pattern from group 3 followed by apply a pattern from group 2, that will save one more clash actually, but not very significant, but still at least some reduction will be there. So, and then after some time, so one of these groups will exhaust. So, when you are alternating between group 2 and group 3, so it is not necessary that they are both the groups have equal number of test patterns in them. So, remaining patterns we have to apply. So, those clashes will be generated. So, the clashes are getting generated only in the remaining patterns, whereas when from group 1 to group 4 transition, one clash will be generated and another clash will be generated at the remaining patterns. So, that way there will be only a few very few clashes that will come. So, within within a test vector, this weighted transition that we cannot avoid, or within a response the transitions we cannot avoid, because that anyway has to propagate through the scan chain. So, we cannot avoid those cases. However, for these clashes we can reduce, and you see one clash contributes to size of chain number of transitions. So, if we can save one clash, so that may be a significant saving in the number of transitions. Another possibility of this transition reduction during scan shifting is by scan cell reordering. So, suppose we have got a 4 cell scan chain where these are the scan chain cells. Now, we finally want this particular test pattern. So, 1 0 1 0 to be shifted. So, initially it is 0, so all flip flops are reset. So, it is in 0 0 0 0, then this 0 is shifted. So, it becomes, so this 0 comes here, then this 1 is shifted. So, the 1 comes here and 0 goes to this point, then again this 0 is shifted. So, 0 comes here, 1 gets shifted and this 0 also gets shifted, and finally, this 1 comes into the scan chain. So, you see, if you compute number of transitions, so here there is 1 2 3 transitions, 4 5 6 transitions. Now, if I can change this scan stitching pattern, so instead of connecting them in this sequence, so if we connect them in a different fashion like this, then you can just go do the same exercise and see that we to get the same pattern 1 0 1 0, number of transitions needed is equal to 2. However, this is not very much practiced, because what happens is that this scan stitching pattern is not always in the hand of the test engineer, because it says that these scan flip flops that we have, so they may be distributed, the flip flops may be distributed in my design at various places. So, if you stitch them in a different order, then it may require long wires, okay, long interconnects may get integrated into the system. So, which the designers may not permit, okay. So, because this delay of these lines and the routing of this interconnect, so that become a problem. So, normally this scan stitching is done in such a fashion that the closest flip flop, so that gets connected to the next to the current flip flop. So, that way the stitching is done. So, this is a problem. So, this scan cell reordering, though it was initially advocated as one of the very promising technique, but now it is not followed much, excepting some situation where we have got the freedom to do this stitching at that reordered. Another possibility is to control the input. Okay. So, what happens is, see, I have said that when the test patterns are going through this scan chain, so the circuit is seeing those transitions. Okay. So, circuit is seeing those transitions, as a result we have got these transitions coming to the circuit. But if I can somehow do it like this, that is, we have got a mask in between and there is an enable signal. So, when this scan shifting is going out is going on, so with this mask will disable these inputs coming to this side. It may be a transmission gate based mask, AND gate based mask, or latch based mask, whatever. So, we do it. So, they actually do not allow these scan chain values to reach the circuit. So, as a result, the circuit will not see any transition. So, this is possible. So, and also it is the case that we can we can put this circuit into some low power mode, in the sense that, so this is my scan chain, this is my circuit. Okay. Now, circuit, as I have said, that when it is idle, when there is no activity at the input of the circuit, so it is going to consume only the static power. It is going to consume only the static power. So, what I have done, I have put a mask here, and this is the scan transition. So, this is the scan chain. So, these scan chain transitions are getting masked off here. So, they are not reaching the circuit. Now, if I use an AND gate based mask, so my mask is like this. So, there are a number of AND gates, and these lines are coming from the scan chain, and we have got this enable signal connected here. So, this is the enable, and this is going to the circuit. Now, when this enable line is 0, so I will see a 0 here. So, the circuit says 0 0 0, but when it says 0 0 0, so it will have some static power consumption, because dynamically the values are not changing. So, dynamic power is not there, but static power will be there. Now, the static power may not be the minimum when the input pattern is 0 0 0. So, it may, depending upon the circuit, so we can have different input pattern that will reduce the this static power. So, it is possible that we put the circuit inputs in some particular value. So, some input control pattern is there, and that input control pattern will be applied to the circuit. So, this situation is modified, like we have got this input control pattern, that may be 1 1 0 1, something like this. Now, this is my scan chain. Now, this is the circuit. So, we put some multiplexers here, 4 multiplexers. One input is coming from scan, another input is coming from here, like this. We can do it like this, and this enable line can be fed as the select line of these multiplexers. Now, what happens when the circuit is idle by enable equal to 0? So, the circuit will see 1 1 0 1. So, which is a pattern for which this leakage power consumption of the circuit is minimum. So, this simulation can be done based on the type of gates that we have in the circuit. So, we can do a static simulation and find out like which what is the power consumption corresponding to the individual gates for different input patterns, and accordingly we can select one input pattern for to work well for the entire circuit. So, this will if we do this, so static power is reduced, at the same time the switching activity gets eliminated. So, there is very little switching activity, when this only switching activity will come when this mask will come into existence. So, at that point there will be some changes, but otherwise not. And these outputs are of course directly going to scan chain. So, if we are putting this capture mode, when we put this in capture mode, then this will be captured into the scan chain. So, there that is not masked off definitely. So, also we can use this in conjunction with vector and or scan chain reordering, scan cell reordering technique. So, that it does not go opposite to that, so it does not cause any harm to that. Another possibility of test power reduction is by vector compaction. So, vector compaction strategies we have already seen, but we can do it in the context of this test power reduction also. So, we have seen that this initial test vectors generated by an ATPG tool is huge, because it initially targets one fault, generates pattern for that, then it targets some other fault, generates pattern for that. As a result, the test pattern set is huge. After that, it goes into a compaction of test vector stage. So, we have already seen that test. So, what we do, if there are two test patterns, one is like say 1 x 0 x 1 0, another is x 1 0 1 x 0, then these two can be merged into a pattern like say 1 1 0 1 1 0. So, it can be merged into a pattern like this, so that it takes care of both the patterns. So, that is actually the compaction, so vector compaction. So, what we do, if we take each of these vectors as a node, and each of these test vectors generated by the ATPG tool as a node, and if two vectors are compatible, we are connecting them by an edge. So, it may so happen that these three vectors are compatible. So, by click partitioning we identify this click, and for these three of them we replace it by a single pattern. So, that technique we have seen. So, in conventional static compaction techniques, these test cubes are merged randomly. So, it randomly selects this these clicks, and then it merges those patterns, but this merging order of test cube pairs can reduce the average and peak power. So, both of them. So, how? Because it may so happen that after, so there may be another pattern which is say this bit is 1. So, this bit is say 1. So, this is there, this is say x x, this is also x. Okay. Now, you see that this pattern is also, let us make it 0, let us make it 0. So, this pattern is also compatible with this pattern, okay, but this is not compatible with the third one. So, if you construct this conflict graph, compatibility graph, so between these two nodes there will be an edge. Now, I have a choice. So, I can merge this pattern with this pattern, or I can merge this pattern with that pattern. Now, which one to do? Now, if I merge this, if I do this particular merging, the pattern I am getting is 1, do not care, then this has to be 0, 1 do not care, then 0, then 0, then 1, then 0. I get a pattern like this. Now, you see that if this do not care bit is still free in my hand, so I can make it a 0. So, if I make it a 0, when it is going through a scan chain, you see there is a transition here, there is a transition here, and there is a transition here. So, 3 transitions I can see, whereas in this case I have got a transition here, I have got a transition here. So, I have got a transition here. So, in this case also I have got 3 transitions, but in general what can happen is that these two mergings, they can give rise to different number of transitions in the scan chain. So, whichever pattern, whichever merging gives us less number of transitions, so I should select that particular merging. Now, there may be choice, there may be trade off, because some merging may be combining a large number of vectors into one. So, that way the test length will reduce, whereas some merging may have very good patterns, so that where the number of transitions are very less. As a result, that will lead to low power pattern. So, we can have a choice. So, we can have a merging order can be selected, so that it can reduce this average and peak power consumption. So, another avenue for this power reduction is via test data compression technique. So, it is test data compression, we know that it is primarily used to reduce the test volume, test data volume that we have to keep in the ATE memory, and also to reduce the transfer time of test pattern from ATE to the chip. So, this we have already seen. Test vectors are kept in a compressed form, and we have seen some codes like Golomb code, Huffman code, etc., to compress the test vectors. So, coding strategy, what it does is that it takes help of this do not cares, it exploits the do not cares such that the occurrence of similar code words increases, and that improves the compression ratio. So, this is the standard technique that we have seen, that any of these coding techniques, so they try to make use of the do not care bits in the test pattern, so that the commonality between these cubes increase, so that they have to store less number of cubes in the dictionary, or the coding can be done. And on chip decoder, so it will decompress the code word to get back the original patterns from the, and then it will be sent via scan chain. So now we can have a trade off as soon as we do this. So how much compression we do and how much transitions it creates. So some of it may be contradictory, like two test patterns maybe they do not care can be filled in two different ways. One way, the test pattern fill up, it may help in the scan reducing scan transition, and filling it in some other way may help in the compression. So we will go back to the example that we had for Golomb code. So we have in Golomb code, we have created, first of all we create these groups of run lengths like A1, A2, A3, A4, etc. like 0, 1, 2, 3 forms a group, 4, 5, 6, 7 forms a group, it goes like this. Now the group prefix is 0 and the tail is 0, 0. So for run length 0, the code word is 0, 0, 0. For run length 1, code word is 0, 0, 1. So it goes like this. Run length 2, it is 0, 1, 0. So it goes like this. Now suppose we have got a test pattern like this. So 0, 1, all these ones, and 0, 0, 0, 1. So here I have got a run length of 1. So there is a single 0. So it is run length of 1. So the it is replaced by 0, 0, 1. Then run length of 1, run length of 0. So that is coded as 0, 0, 0. All these are coded as 0, 0, 0. Now this part, it's a run length of 7. Okay. So it is a run length of 5. Sorry, this is a run length of 5. So it is replaced by the code 1, 0, 0, 1. So as a result, this original pattern set was 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12 bits. So that has been coded, 12-bit pattern has been coded into a 19-bit pattern. Okay. In this case, the code length is more than the pattern length, but of course we have seen previously that it can reduce this code length is generally much less than the pattern length. Now suppose I have got one test vector like this. So this is the ATPG tool, it has generated a test vector like this 0, 1, then 3, these are all do not cares, then 1, 0, then again 3 do not cares, then 0, 1. Now if I want to reduce this weighted transition metric, then what I should do? I should try to minimize the transitions that are occurring in between. Since this is 0, I do not want transitions. So here actually both the sides are 0. Okay. So this is also 0 and this side is also 0. So that immediately suggests that all these x's, they should be filled with 0. So I get it like this. Similarly, this group of x's, so it is bounded by 2 ones. So they should be filled up with 1s. So this is the test pattern that we will get if we want to minimize the weighted transition metric. And if we code this particular test vector, we can see that this Golomb code length will be 19 bits. Okay. So it is not shown here explicitly, but if you do the exercise like finding the runs of zeros and then coding it using the table that we have shown previously, so the length will become 19 bit. Whereas for if you compute the weighted transition metric for this pattern set, so it is 18 by using the formula that we have discussed previously, the weighted transition metric. So that is equal to 18. Now what about if these do not care bits are filled in such a fashion that this compression is aided. So for aiding the compression, what I would like to do is I would like to since this Golomb code is based on runs of zeros. So I will try to increase the runs of zeros. So this part is filled, the first part is filled as we have done here, but the second part we fill with zeros, because that will give me a run of 3 zeros. Okay. It will give me a run of 3 zeros, and in this case if you do the Golomb coding, so the code length will be 10 bits. Okay. So code length reduces, but if you compute the weighted transition metric for this particular case, it will turn out to be 25, because it will be shifting from this side. So as a result, it will be turning out to be 25. On the other hand, if say another example, say this pattern, then again the same thing. If you fill it up for minimum weighted transition metric, so this will be the fill up, and Golomb length code will be 27 bits and weighted transition metric value is 23. Whereas if you are filling with for compression, then this code length can be 13 and transition metric value can be 32. So that way there is a huge difference. Okay. So so we have got the trade off, like which pattern we choose for which purpose. So that has to be traded off. So it depends on the choice of the test engineer, it depends on the amount of memory we have, it depends on the power budget of the chip. So, depending on all those parameters, so we can select the appropriate mechanism. Next one is, when are we going to change the primary input? Okay. So, as I was telling that every test pattern, so it has got a number of primary inputs and number of scan inputs, the pseudo primary inputs, and in a scan environment. So, these scan inputs are fed in a serial fashion through this scan chain. Now, when do we apply this test pattern? This test pattern we can go to the launch and capture cycle only when this entire shifting has been done. Okay. But this primary input part, it can be changed at any time from the shifting of the first bit till the shifting of the last bit. So, at any point of time we can change this primary input part. So, what is the best input pattern? So, when should the primary input be changed to minimize the number of transitions in the circuit? So, if there are m number of scan cells, then this this pseudo primary input part yi is shifted in m clock cycles, and primary input can be changed at any of those these m cycles without affecting the test efficiency. So, when are you going to change the primary input? So, that is the concept of best primary input change time, and in fact, there is no straight cut guideline like when this should be changed, but this depends on the circuit to very much. So, maybe we need to do a proper simulation of the circuit to see when this primary input is going to change, when this primary input should change, so that we get the minimum power consumption. We will continue in the next lecture.